What I want to do is give you a sort of brief look at this whole concept of participatory sensing. I'm sure some of you have already heard of it, perhaps worked on it. And I know all of you come from different backgrounds. So I'll kind of assume just that no one sort of works in this. So I'll go through some brief introduction. So if you work in this area, please bear with me. And then I'll get into some of the research we do. So I come from University of New South Wales. As I said, we're based in Sydney. Some of this work is done in collaboration with a number of researchers from TU Darmstadt, CSIRO, which is a government-funded research organization in Australia, NEC, and I2R from Singapore. Right, so I'll start off with some basics. I'll give you a sort of broad overview of the research we do at UNSW in this space. So you just get a glimpse of the research challenges in this space. And then I'll get into one specific system that we've developed. As the name suggests, this has to do with sort of building a noise pollution map of a city using smartphones. And then I'll conclude with some future directions and open challenges. Right? And please feel free to interrupt me at any time, okay, if you have questions. You don't have to wait till the end. I know I'm starting about 15 minutes late, so let's see, I might end early or we might just spill into the coffee break. Okay, so since this is an IoT school, I'm pretty sure all of you have heard of traditional sensor networks, right? So we have these small devices, you embed them in the environment, and you can collect a lot of interesting things. I mean, this area has been active for about 15, 20 years now, so there's certainly a lot of research that's already been done. And there are quite some interesting applications already, right? So you see real deployments of sensor networks for things like wildlife monitoring. So for example, we did a project with CSIRO where we put these collars on these cows, right? And when these cows sort of left the fence, so instead of putting a physical fence, we had a virtual fence. So when they moved outside the designated region, they were given a slight electric shock, so they could come back, right? So you could do some of these interesting things. Currently, we are doing a project on monitoring flying foxes, which are essentially bats that roam around Australia. And then applications of sensors in things like monitoring volcanoes, earthquakes, drones are becoming very popular. So really, I mean, there's huge applications of this already. And this will all certainly continue, but most of these applications, as you see, aren't directly necessarily related to us humans, right? Because you go and deploy this outside. So you don't really see applications necessarily on a day-to-day basis. And the reason, of course, is because people are out of the whole sensing loop. And then a few years back, we had this wonderful device that was put out there, right? And so this is essentially a human sensor, right? We carry this device on us. And if you open up the spec of any smartphone, I mean, this is still a bit dated, but still you see a wide variety of sensors, right? So you have your displays, you have your haptic feedback vibration sensors these days, touch sensors, you have your accelerometers, location sensors, proximity light sensors, multiple cameras, multiple microphones. So it's really a sensing platform in a sense. It's you can, of course, I mean, the main purpose is to make phone calls and browse the web, but clearly there's a wide variety of things you can do beyond just basic cell phone use. And now you have this whole new range of external wearable sensors, right, that's coming up. I believe Apple is due to announce something next week, right, I heard. And then you have other smart watches or smart bands. You have wearable body sensors, fitness monitors, augmented glasses. So essentially you have kind of this whole sensing ecosystem that we humans are actually carrying around with us, right? So you can actually leverage this, connect it to your phone and get a fairly decent indication of what's happening around you, right? With you and around you. And the possibilities are quite endless, right? So you can infer your physical activity, Your basic things like you're walking, running, sitting. You can get a sense of your social interactions. So the phones that you're carrying can perhaps detect who you're seated next to, who you're sort of conversing with, right? And learn about your social interactions. And you can infer a range of things, right? So here I've just put down sort of few things you can infer. So I talked about social networks. You can detect which group of people are co-located, how often you're actually conversing in a group. We did actually some experiments with this in an undergrad project where we had this phone monitor and sort of figure out who is talkative in a group, right, and who's kind of silent. And it gives you interesting insights because you might not think you're perhaps a silent person or perhaps you're a talkative person. You can learn about tones, and from those tones you can detect a lot about emotion, right? Because the same thing could be said in different tones, and it could have different meanings actually. You can detect if a person is a loner. You can try to sort of infer the emotional state. Again, an interesting project we are doing here, sort of trying to get some early signs on depression based on how you use your phone. Ambient noise, which is what I'll focus on. Modes of transport, what sort of restaurants and bars you go to, so that infers your social life. And then some high-level inferences about the things you do, right? So these are some basic inferences, but then you can go up one layer above and do things like, can you detect actually whether I'm cooking based on the things I'm doing, whether I'm reading a book and so on, right? Watching TV. So you can infer essentially a lot of things, right? And this is just about one individual person. Now you multiply that with 7 billion people essentially, right? So you have this huge density of these devices that are carried around, particularly in urban environments. Some other factors that contribute to mobile crowdsourcing are programmability, right? Back when we've been doing this research for the past 5 years, before even the iPhone was launched. So the early experiments we did were with the Nokia phones, and perhaps you've worked with them. They are not very easy to program, right? But that has changed radically these days, right? So you have, the SDKs are wonderful. It's very easy to write applications, right? And students want to do this, right? I'm sure some of you are already doing this. So it's very attractive to actually develop applications. And you can do a bunch of things these days, right? Multitasking and things like that. The hardware is quite advanced. If you look at any phone, they've got at least a 2 gigahertz CPU or more. You've got multi-core processors these days on these phones. You've got good RAM, good memory. There's really no limitations these days, right? It's just like writing code for a desktop, essentially. Then the distribution platform has matured quite a bit, right? So you have these very nice app stores out there, and you can create your app, you can put it out there, and perhaps it gets some traction, and then people download this. So it's very easy to actually distribute these apps, right? And this can actually be useful because as researchers, if you do a decent job, you get some traction, you can actually collect decent amount of data for your research, right? Just by having your app out there in these app stores. And then of course you have the cloud, right? The back end. I mean, ideally, yes, you want to put everything on the phone, right? You want the phone to be as intelligent as possible, do all the inferences there. But clearly there is one fundamental limitation, which is energy, right? I'm sure all of you have had problems with your phone dying suddenly in the middle of the day, right? I need to charge my phone every day, sometimes twice a day to get through, right? So certainly while we want to push as much intelligence on the phone, there are some limitations, right? So what you could do, and what is usually done, is you do some basic inferences here on the phone, and then you push the complexity into the cloud, right, where you can do more sophisticated processing, right? You can do number crunching and so on. And this is again fairly easy to set up, right? AWS, and there are a bunch of other cloud platforms, backends that you can use for this. So if you look at all of these, right, enablers, and you put them together, you can actually create a very large scale sensor network essentially, right? You have 7 billion sensors out there, and they can be used to sense what people are doing. Right? And you can get some very cool inferences from this. So I'll flash through just a few applications, just to give you a sense of what can be done, okay, before I get into some of the tech stuff. So this is something we did a couple of years back, Haze Watch, right? Your phone, at least for now, doesn't actually have environmental sensors in it, though there are talks there could be in the new phones. But what you could easily do is you could make a small box like this. So this was something we got made in China. Just a small box where we put in some nitrogen dioxide, carbon monoxide, and ozone sensors, and then a Bluetooth transceiver, which could then talk to the phone. And then you could mount this on your car, drive around, and you get a very nice view of the environment, right? The pollutants, essentially, that you're being exposed to, right? So this gives you essentially your personal environmental footprint, essentially, right? Exposure footprint in terms of these pollutants. So you can build nice pollution maps within the city. Now you might ask, why do you want to do this? Doesn't the city already do this? Well, they do. But for example, in Sydney, we only have 12 or 13 environmental sensors that are deployed by the city, right? So though that gives you a good high-level view, it doesn't give you a microscopic view of your personal exposure to these pollutants. And then if you crowdsource this data, so people share this data, then you can build some nice apps where you can estimate your exposure plot, right? So if, say, you drive along this particular route to work, or cycle along this route, you could go and check what's the typical pollutant exposure along those paths. So it gives you some nice insights, which can be quite useful for medical purposes. Traffic monitoring is a very sort of active and widely used area within crowdsourcing. So I'm sure you've heard of the Waze app, right, where people can sort of indicate if there are traffic jams, if there are accidents, if they see a police with a radar gun somewhere along the road, right, and inform other people. There's a bunch of work done in Berkeley, MIT, and places like that to monitor road conditions as well, right? So MIT had this project on pothole monitoring. So to detect the potholes based on the vibrations your phone experiences as you're driving. Right? And again, this can be shared with the municipality and with other people. Right? You can do some interesting citizen sensing applications. This is work done at UCLA, where they asked students in the university to take pictures of, say, how full the garbage bins are. Right? I mean, you could certainly send out people to do this, but that takes up time and effort. So why not ask students who are walking around on campus anyway, right, to contribute? So you could sort of monitor the occupancy level of trash bins around campus. They've done some other work in things like looking at flowers in national parks there. So hiking enthusiasts can share pictures of what sort of vegetation is blooming and so on. So there's a bunch of interesting apps here. And these are kind of motivated by the citizens themselves contributing. So that's why you have this sort of participation happening here. So you'll notice there's some sort of slight subtle differences. So some applications are what we call opportunistic, in that they just keep sensing in the background. And then some actually require active user participation. So things like taking pictures, for example, requires you to actually participate in the process. Okay? And then health and well-being is, this is more a personal thing, I would say. You necessarily do not want to crowdsource your blood pressure readings, right, to the general public, but it can be useful for keeping track of your own health and sharing it with sort of medical professionals. Right? So in that context, you are still crowdsourcing some aspect of it. So you can build some nice, perhaps some of you use this. I use this app called Move, for example. Right? It gives me a nice view of how much time during the day I'm just sitting, right, on my butt in front of a screen, and how long I'm actually walking and doing some exercise. So this gives you some interesting insights about what you're doing on a day-to-day basis. Okay, now there's certainly opportunity for coming up with some business ideas here. So there's been a bunch of startups. You might have heard of these. So there's this company called GigWalk, a startup in the US, where the idea is if you want someone else to fulfill a task, you post a task and you promise to pay a certain amount. So, for example, here someone is asking the community to verify blocked road, right? And they're paying $4 if you do confirm this. So you can sort of create these sort of tasks on mobile devices and get people to contribute. I believe Microsoft Bing actually widely used GigWalk to collect. They have this similar thing like Google Street View, right, where they got sort of street photographs, panoramic pictures of street intersections. So they actually used GigWalk to crowdsource this data. And then there's some other. This one I think is based in the UK, a company called Field Agent, which is kind of similar. So there's certainly a business case if you can make one with this particular approach. Okay, so that's just my introduction. Now, when it comes to research challenges, right, as PhD students, you of course want to know what are research challenges that you can work on. Now, since I personally come from a traditional sensor network community, my research was initially, I mean, it's still based around this. It's important to understand that the research challenges are very different here, right? Because what we are doing is we are using existing sensors on mobile devices, and then we are using existing networks to collect this data, right? So there's no real networking issue here, right? The research challenges are very different. It's more about the data, right? How you understand and interpret the data. So machine learning is a very important aspect of research here. How do you optimize the data collection, right? Because phone battery is, you have to conserve phone battery. So how can you make things more energy efficient is an interesting area of research. As you may have guessed, privacy is very important because you're asking people to share data. So why should they share data? What are the implications of that, right? And then data quality, because all said and done, the sensors on your phone are not very sophisticated, right? They're fairly low fidelity sensors. So how can you actually get good quality data based on that? And how can you trust the data, right? Because someone can easily game the system and start contributing bad data to their own benefits, right? So these are some challenges, and I'll talk a bit about some work we've done in some of this. And then, as I said, I'll focus on one particular application just to give you a sort of view of what actually goes in building a real application. Okay, so as I said, we've been working on this for a good 5-6 years. So we've had several PhD students, undergrads, and postdocs working on various aspects of this, right? So we've done some, I think, some reasonably good work. So I'll go through some of the key contributions we've done. So we've looked at several actual applications and systems. So a few years back, we came up with this system called Petrol Watch, which essentially was to share fuel prices as you. So the idea was to do this in an automated way, right? You could certainly ask people to actually enter in the fuel price that they, for which they've filled up fuel, but that clearly involves user participation, and people may not want to do that. So we came up with an automated system where the idea was to put the phone on the dashboard with the camera facing out. And then as you approached a fuel station, because the phone has the GPS and you could easily pull out on a Google Maps, for example, where all the fuel stations are. So as you approach a fuel station, the phone camera would turn on. It would take a bunch of pictures of the billboard here as you pass by, and then we could extract the text from this and upload it to a server, right? So we did some nice experiments in Sydney and got some decent results from this system. Another piece of work we did was mapping network bandwidth. As you all perhaps know, the bandwidth, especially if you're moving around in a vehicle, right? The 3G or 4G network bandwidth varies quite a bit because there are various terrain properties that determine the bandwidth you experience, right? So given that, you can, especially if you're doing streaming, for example, or something that's bandwidth intensive, if the bandwidth fluctuates quite a bit, then you're going to see poor performance, right? So we thought, okay, why not build like a bandwidth map of a city, right? So as you're driving around, you do some measurements, and then you try to estimate roughly what would be the bandwidth along different sections of the road. And if you had this knowledge, you could then perhaps tune the video streaming applications, right? So that you can adjust the quality as you're moving along, right? So we've built this app to collect these network measurements using two approaches. So one is what we call an opportunistic approach. So whenever the user actually uses his mobile device for browsing, in the background we measure the bandwidth that you're experiencing. And then we also had an active approach where we were actively sending probes to measure the performance. There are obvious differences. I mean, this gives you better results, but this is more bandwidth heavy because you're actively probing. And then we did some experiments to build these maps. And then we showed how these maps could be interfaced with a streaming application, whereby you could adjust the quality based on the map. And we've got some good results with this. Another application, yeah, good.
Yes, I'm going back to the 3G, 4G
yeah.
Are these information used for yourself or for other people?
Right, so you could certainly do this on a personal level, right? So you could create your own personal map, which is quite relevant to you because usually we take the same roads as we drive around. But you could also certainly crowdsource this, right? So if you build like a city crowdsourced map, then others could benefit from your measurements. And we've used both approaches here.
And did you see lots of fluctuation? Because it could be, I mean, the throughput issue could be because you have bad coverage or bad signal to noise because of the terrain, but it could be also because there are a lot of people using the link at that time. So we know that when you're going to measure on a near real-time basis the available throughput, you can be a little bit too reactive to this kind of things, and then you will end up with very unstable behavior with oscillation.
Yeah, that's true. So we've done some work looking at these issues. So one thing we found was time of day can help. So it's not just the location, but at this location during peak hour, right? So you could actually adjust the map based on that, and that gives you a fair indication of the load in terms of how many users typically connect to the same stations. And yes, there will I mean, you can never predict with 100% accuracy, right, what bandwidth you get, but what we saw was, okay, even if we had, say, the mean and some sort of idea of the distribution, knowing that, you could get better performance than just using the reactive approach. So that was the idea. I mean, yeah, you're right. We'll certainly never exactly know what's happening. Okay, another application we did was measuring your carbon footprint, primarily focusing on the modes of transport you take. Right. So based on your day, say you took the car for 1 hour, took the bus for whatever X minutes. So based on that, you could kind of estimate what impact you're creating on the environment based on the modes of transport you take. And then if you share it with other friends, colleagues, you could perhaps motivate each other to be more green. So we did some experiments on our campus with some success on this. So yeah, that's just a brief look at some of the apps and systems we've developed. Another piece of research we've been doing is looking at the trust aspect, right? So I earlier mentioned the fact that, okay, you're asking people to contribute. Well, couldn't people then start contributing bad data, right? And what are the implications of this? And bad data could come through in two ways. One is just due to the poor fidelity of the data, of the sensors, right? So for example, this shows you a very blurred image, right, which may not be very useful in terms of, say, extracting the text. And the other reason could be just bad users, right, malicious users who want to game the system. So how can we actually trust the data? So we've done some work on coming up with a trust framework, a reputation framework essentially, where you can attest a reputation score to each sensor for a particular user, and then you can build a history, and based on that you could perhaps filter out some of the bad data that's coming in. Right? So we've got a bunch of papers on this. I won't get into the details. I just, as I said, wanted to give you a brief look at some of the research challenges. If you're interested, you can find these on my website or just email me, and I'll be happy to point you to these. So another issue is privacy, which is, it's a very big issue, right? Because you're asking people to contribute geotag data, right? And based on that, you can infer actually a lot of private information about various people. So we've done a survey where we've looked at what are the implications of these sort of applications, right? And surprisingly, it's quite scary, right? You can actually, just by looking at some background information and some sort of footprints, you can actually figure out who an actual person is when they're contributing this sort of data. And location is really the key here, right? Because once you're contributing geotag data, you can actually infer a lot about people. And there's been quite some uproar in the media recently. There was this story about Apple sort of tracking users. Similarly, Facebook has come under fire for this location-aware mobile app. And I'm sure you've heard a bunch of stories in the media about this. Right? So it's certainly an important issue. And as I've earlier mentioned, the reason being, if you start contributing geotag data as you're moving around, right, you can actually build sort of a history of your travel pattern, and then you can figure out where you work, where you stay, what are the important locations you visit, and that can reveal a lot about a particular person. So again, we've done some work in this space. So one particular piece of work we did with TU Darmstadt was trying to sort of jumble your location tracks, right? So rather than contribute your directly your actual data, you jumble it with other users, so that when this data is then uploaded, you're not actually uploading your own data, but it's mixed with data from some other people. Right? So that was the basic idea. When multiple users sort of are in the vicinity of each other, you exchange some of your sensor readings with others, so that you confuse the backend, right? So no one can actually infer your true path. So for example, if these are the true paths for these two users, right? When they meet, you can exchange the paths so that based on the exchange strategy, this is the what gets uploaded for this user, and this is what gets uploaded for the other user, right? So you can't actually infer what are the important locations for either of those users. And we did a bunch of experiments to sort of figure out within this design space, right? So you have two things. One is how often do you exchange readings with other people, and then how do you report the readings back to the backend? And we looked at various strategies to figure out what are the optimal practices. Okay. Another thing we were looking at is, okay, I earlier talked of this reputation system, right? So you want to certainly build a reputation of users, right? But at the same time, you want to protect the user privacy, right? So we found that there's actually a clash here, right? So when you're trying to protect user privacy, there's, again, a bunch of approaches, right? So one is you could use a mixed network where you route the data through various proxies, essentially like Tor. You could use pseudonyms. You could use anonymization. So this was, again, some earlier work we did. And then you could use the data jumbling approach. Right? So there are various strategies for this, but the key here is we are trying to dissolve the links. We are trying to sort of break up the paths. that are taken by the individual users. And then if you look at reputation, well, you're trying to do the exact opposite because you want to sort of build a history of the user, right? So there is this tension between privacy and trust that we found. So the problem was how can we have both, right? Because both are important. So we've done some work in this space trying to come up with a reputation system that still preserves your privacy. Now this is based on blind signatures and some various other concepts. I won't get into the actual details. You can look these up in some of our papers here. Right. Yeah.
But if you are doing like this, then you are losing this real-time notification system. I mean, if you have to wait until you meet some other participant to share your data, then you will not be able to give the real-time alert. So, so how can user benefit from the system? For example, if the air pollution or something is bad, this part of the street, and he went away, so it's not useful information for him anymore.
True. You're right. So certainly this will, because there is some delay, right, essentially in uploading the reading. So it won't necessarily work for real-time approaches, and in that case, you could use some of the other approaches. So the idea of path jumbling really only works for apps that are sort of okay with some delay. Right? For other approaches, you might use things like a mixed network, which has little lower delays and things like that. Yeah, that's a good point. Okay, so yeah, that's privacy, right? So the next thing we were looking at, the next issue was how do you motivate people to contribute, right? This is again a very big problem. We've experienced this several times. I talked about some of the apps we developed, and then when we ask our PhD students to go out and test, it's certainly everyone wants to participate because it's our PhD students. But when you give this to random people, right, the obvious question they ask is, why should I contribute, right? So we've looked at this interesting problem in two ways, right? So one approach was, okay, can we leverage of the social networks that we create, right? So for example, if I'm interested in collecting some data, right, let's say environmental pollution. So perhaps my friends would be more motivated to contribute data for me, right, rather than some random person on the street. So we've looked at this interesting sort of combination of social networks and participatory sensing, right, and how we can sort of explore that to encourage people to contribute. And within that, we've done some work on coming up with a trust model. How do you trust the data that's coming from your social acquaintances? How do you recruit your friends? Because clearly, if you look at social networks, we friend a lot of people who are not necessarily our close friends, right? That's pretty typical. So how do you actually trust the data that's coming in? How do you recruit good participants? How do you still preserve privacy? So some interesting work that's been done in this space. Another angle for this research is, as I mentioned, okay, why should I contribute data, right? Because it involves some effort, right? It might be direct effort to do the data collection, time, the battery, your bandwidth, your privacy. So what do you actually have to gain? So we've been, again, looking at social notions. So there's this notion of nepotism, right? So if you look at, on this particular scale, if you only care about yourself, you're egoistic. If you're completely altruistic, I mean, you go out of your way to help other people, you could be called altruistic. And usually most of us tend to fall somewhere in the middle, right? Which is usually called nepotism. So this simply means you work for the people you care, or the work for the people you love, right? So you're happy to usually go out of your way to do a few things for your friends, for your family, but you wouldn't necessarily do that for some random person, right? So this idea was very recently presented where we came up with a system called an endorsement web. Right? So you sort of create a web of participants where users can actually endorse each other's contributions. And based on those endorsements, you can then trust people who are viewed favorably by others. Right? So it's some interesting, this is a bit sort of theoretical work where we work with some game theory scientists to come up with this model, but we are now looking at how we can actually implement this in a real participatory sensing system. Okay, so that was my sort of broad look at some of the research we do, some of the challenges that exist in participatory sensing. Now, what I'll do is go under the hood of one particular system that we came up with, which was to monitor the noise pollution in a city. So this was work done with some people at CSIRO and Portland State University. Okay, so noise pollution. Why did we pick noise pollution? Well, it's a well-known problem, especially in large cities. Perhaps not so much here in Biograd, but certainly in Sydney and some other big cities, right? You have all these construction sites, you have a lot of traffic, you have airport, planes flying over the cities. So a bunch of noise hazards out there, which we are constantly being exposed to and which we are not even aware of, right? And there has been research which has shown that all of this can actually have a bad impact on us, right? It can lead to hypertension, hearing loss, sleep disorder, and a variety of other problems. So now the question is, okay, how do we try to solve this problem, right? And in order to do this, the first thing you need to know is what are the noisy hotspots in the city. So this shows you a map of London, and this shows you, it's perhaps not very clear, there's a scale here. The colors indicate how loud the various parts of the CBD are in London. Right? Okay, so that's the first sort of point of attack, right? Try to identify places that have large problems with noise. So now the question is, how do you generate this noise map, right? So the current traditional approach is, okay, we do a computer simulation based on things like the road traffic, the type of cars, the vehicle types, and so on, and build a estimate of the traffic noise. So this is actually not a real noise map. This is an estimated computer simulation. Right? So this certainly gives you a good high-level view, but again, it's not necessarily very accurate, right? And it may not be specific to individual users. Right? So another approach is, okay, go and deploy a sensor network in the city. Right? So place sensors all around the city and collect static sensors and collect data. Well, certainly that will work, but the question is, who is going to put in the money for that, right? City councils are already, they don't have funds, right, to do all this sort of stuff. So while in theory this will work, in practice it's certainly not going to pick up. So an alternate approach, or something that could perhaps be combined with some targeted deployment of static sensors, is to use mobile phones, right? Because people are walking on the streets anyway, so why not get them to collect street level audio samples, right? And this scales very well because people move all around the city, so you can get very nice spatio-temporal coverage. Okay? And the update latency is much smaller because you can get people to contribute every day, and then you have a very nice near real-time map of the city. But clearly there are challenges, right? I mean, yeah, at the high level this makes sense, but how do you go about actually implementing this, right? So one challenge is, okay, while people do move around, they may not always contribute data, and so you may not get data from all locations in the city. You certainly don't have control, right? You can't actually ask people to go and to specific routes and collect data for you, right? No one's going to do that for you. This is again important. Certainly while you're collecting the data, you do not want to compromise the primary use of the phone, right? A user should be able to use the phone as he or she wants it, they want it, right? So it shouldn't interfere with any of the usual tasks. A practical issue is the microphone may not be exposed, right? So if you're carrying the phone in your pocket, you're going to muffle the sound. So, or if you're carrying it in your bag, you're not going to get good readings. So that's an issue that must be addressed. When should the measurements be collected? And the most important one perhaps is, can you actually get decent readings, right? Can the phone actually work like a commercial sound level meter to begin with? Right? So we've tried to address some of these issues. So we kind of take a three-pronged attack. The first one is actually trying to make sure that you can actually build a sound level meter on a phone. The second issue was this issue of context, right? So you, as I said, you only want to collect data when the person is in the correct locations, when the phone is in the correct location. So can we build a context-aware system that triggers this? And the last issue is how do we deal with incomplete samples, right? So can you actually reconstruct the noise map from some random incomplete samples? And then other issues are, okay, what about power consumption, right? How much battery does this take up, and so on. Okay, so let me get into some of these specific issues. Okay, so this shows you the high-level architecture of our system. So this block up here is what's implemented on the phone. That's our backend. And this also shows you two modes of operation. So one mode of operation is when the user is actually uploading data. Right? So that's the data collection part, which goes through here. And then down here you also see a query system. Right? So let me talk very briefly about this and I'll get into some of the details. So up here you'll first notice the first thing we do is we detect if a call is in progress, because obviously you don't want to collect data when the person is talking on the phone. If the call is not in progress, then we have this context detection module, which detects the correct context for doing the measurements. And I'll mention this later. We look at the accelerometer sensor, the proximity sensor, and the GPS to detect this, because the way what we are focusing on is street level noise. So we only want to take measurements when a person is actually walking outdoors, right? Not when he or she is inside a room. So for that we use the GPS. Now assuming we are in the correct context, the phone will then trigger the signal processing module, which then starts measuring the noise level. And then these noise samples are geotagged with the location and time, and then get stored in the phone memory. And then periodically these noise samples will be uploaded either through Wi-Fi or 3G to the internet. So in our system, we were only uploading data when the phone was in a free Wi-Fi hotspot, but you could certainly change this and do real-time updates if you wanted to. Now, once the data reaches the backend, here you'll notice we have a communications manager, which is simply waiting to hear from contributors. Then here we do some sort of grid-based interpolation, which I'll talk about later. And then we store the data in an SQL database. Right? And periodically we run what's called a reconstruction module to look at this data and then create an actual map using some interpolation techniques. So that's the data upload part. Now the query part is kind of similar. So let's say a user wants to know the noise levels along this particular street, right? So the user would send a query. The backend would map this location over the noise map and then pull out just that part of the map and send it to the user. This was done using Google Maps. Okay. Okay, now let me zoom in again and look at some of the more specific parts of the system. So I'll start off with the, oh yeah, good.
So if I understood well, you said that when you're not going to make the sound measure when you have a call in progress, right?
Mm-hmm.
But usually when you don't have a call in progress, your phone is somewhere in your pocket, your clothes, or maybe you're going to explain this later on, but I guess the sound level would be modified in some ways. Whether there may be another thought is when you have a call in progress, you're sure that you have your handset outside your pocket, at least, and maybe you could detect silence, and then at that time take the environmental noise that is not disturbed by phone being in your pocket or something.
Yeah. Okay, I get what you're saying. So you're saying as long as the phone is still exposed. One issue we had with that was since it's very close to the person's mouth, the speech will kind of drown out the surrounding. So it kind of creates, it doesn't give you an accurate picture of what's actually happening in the surrounding. But yeah, you could look for periods of silence and only extract. Yeah, that could be an interesting extension. We haven't looked at that. The practical issue I see with that is whether we can actually record sound when a call is actually in progress. That I'm not sure on the phone. Because
the microphone is on because
yeah.
you're ready to speak.
Yeah. But yeah, could be looked at. Okay, so I'll start off with the sound level meter, right? So how did we actually go about measuring sound? Now, if you look at sound, this whole acoustics research, right, you'll see that there are various ways to actually measure and quantify sound. There are various weighting systems, as they are called. Now, when you focus on the impact of noise on human health, there's a very specific weighting called A weighting, which is normally used to measure sound. And this is measured in decibels using what's called an LA equivalent measurement over a certain period T. Right? T is the duration for which you sample. So the way this, so imagine this is the actual sound pressure level, right? The actual signal. So LA equivalent T is simply the average of this over this time T. So imagine you have a constant sound source of this value over time T. The total energy here is the same as the total energy under the actual signal. Right? Okay, so how did we actually implement this, right? So when you're actually doing these measurements on the phone, what you're actually measuring is the induced voltage in the microphone. So what we did was we implemented a 10th order digital filter. I won't get into all the signal processing details. If you're interested, we can talk offline. But essentially we took the voltage, we passed it through an A weighting, and then we computed the LA equivalent in decibels. And in our case, T was just 1 second. So we were doing this every second. Okay, now the other issue was speech detection. Now, what I mean by that is, again, our focus was trying to measure street level noise that's caused due to traffic and other external sources of noise. So we actually wanted to filter out human speech, right? Because when you're walking on the street, sometimes other people might be talking around you, and that might corrupt the noise samples. So we first tried to test this out. So here we set up a simple experiment where we had two phones with our system implemented about 5 meters apart on a road. So both phones were exposed to the same traffic noise. But near one phone, we had a group of volunteers talking, right? So that particular phone was measuring traffic noise along with speech. The other phone was just measuring traffic noise. And this shows you the spectrum, the amplitude at various frequencies. And you'll notice there's a distinct difference between the one that's corrupted with noise and the one that's pure traffic noise. So in our case, yeah, we could certainly try and extract out the speech from this, but that proves to be a bit challenging. So what we decided was, let's just neglect these samples and just account for these samples. So we needed a way to separate out the measurements which had speech included in them. So we looked at various features using this data, and we looked at median, mean, and so on. And we found that the median amplitude of this signal was sufficient to separate the samples which had this speech from those which didn't. And we tried this out with different groups. So whether it's a female speaking, whether it's a male speaking, and so on. And during off-peak traffic hours, during peak traffic hours. And you see a very clear separation between the samples corrupted with speech and those that are not corrupted with speech. Right? So just a median detector was sufficient.
Sorry, is it focus size or something? I don't understand. only the traffic flows. There's a peak in, somewhere in
Yeah.
400.
Yeah.
Why don't we see this peak on the traffic flows with?
Yeah, because there might be some negative, because they're not necessarily additive, right? It's not digital, right? It's analog. So there might be some destructive addition happening which moves that peak here. Yeah, that's certainly something we explored. Okay, so yeah, we used a simple threshold-based detection, and I'll show you some results later for all of these. Okay, the next was context, right? So I talked about this earlier. So we looked at a survey done by Nokia, and they found that, okay, these 4 locations, and kind of makes sense anyway, right, if you look at it. These 4 locations are the most typical places where people carry their phones. So these days, belt pouches have kind of faded out. I mean, it's very hard to carry large phones on belt pouches these days. So I would kind of just focus on the first 3. Okay, so which of these are good locations for doing measurements? So what we did was, I think we had about 10 people. We asked to collect data. So we asked these participants to carry 4 phones one in each of these locations. And we also had a reference sound level meter, which the person was carrying in the other hand. And then we sent them out on the street and did some measurements during peak and off-peak hours. So this shows you just one snapshot of the actual data. The reference is the actual sound level meter, and the red line is for the phone. And when you look at this, you very clearly see that when the phone is in the hand, you typically get very close approximation of this sound, right? Which is kind of expected. When the phone is on the belt or in the pocket, we actually, for some strange reason, we saw a shift of about 10 seconds, I think, in the measurements. We still don't know why this happens. And then if the phone is in the back, we get completely muddled readings, which is again expected. Okay? So based on this, we said, okay, why not just play safe and only take measurements when the phone is actually in the hand. Now you might say, okay, when do people actually carry a phone in the hand and they're not talking? Now you go out on the street and just look at how people walk these days, right? And I'm sure you do the same, right? People are just walking like this, looking at their phone rather than actually looking at where they're going, right? So you can actually get a decent set of samples by just focusing on the hand position, right? And not worrying about these. Oh yeah, so these are peak hour and then these are off peak. And you see kind of similar trends here, right? I'll skip this. Okay, so this shows you the measurement accuracy in terms of the RMS readings, the mean square error, for the peak and off peak and for different positions, right? And in this case, we tried to even remove this lead, the time lead that we saw. And again, based on this, we concluded that the hand position is the best. You'll see that the mean errors are less than 3 dB. And it is known that humans cannot actually perceive a difference of 3 dB anyway. So this was the best option for measurements. Okay, now given this, how do we actually design a practical system that can only take measurements when the phone is in the hand? So what sort of sensors would you think about, right? So we looked at, we asked again a bunch of people to carry a phone. So what we did was we asked each candidate to go through this particular sequence of phone positions. So they held the phone in their hand for 1 minute, then they switched to the bag, then they switched to the hand pocket, so on. Right? And we gave them a timer so they could time for how long they're doing this. And we collected some data from 3 different sensors. So first was the accelerometer. So these 3, X, Y, and Z. The bottom 3 are the readings from the accelerometer. The next 2 sensors we looked at was the proximity sensor. So on your phone in the front, there's usually a proximity sensor that detects if there's another object in the proximity. And it's a simple sensor which gives you two values, a high value when something is in proximity and a low value when something is not in proximity. So that's shown here, the purple one. And then there's also a light sensor at the top here, which helps with your camera. And that returns a reading between 0 and 100. 0 indicating dark, 100 indicating very bright. And that's shown in the black lines here. And for some reason we found this light sensor wasn't very useful, especially when you're cycling through a bunch of positions. So we neglected the light sensor completely. And then we focused on the accelerometer and the proximity sensor. Yeah, okay. So now looking at the accelerometers, right? So we looked at all the different axes. So here we plot the distributions for the x, y, and z in different positions. And you'll see that the z-axis was sort of the one that gave us the best fit with a normal distribution. So here we thought, okay, let's try and focus on the z-axis. And then we looked at various features for the z-axis. Remember, our goal is to detect whether the phone is in the hand and only trigger measurements when the phone is in the hand and disregard the other positions. Right? So we essentially want a binary classifier. Is the phone in the hand or it's not in the hand? So for that we looked at various features for the z-axis, mean, median, different percentiles. And we found that the mean was a good indicator already. Right? So for example, if you look at this particular threshold, you'll find that whenever the z-axis is above that, the readings for the accelerometer, then it indicates that the phone is in the hand. Otherwise, it's not. Right? So it was a fairly good, simple sort of feature that we could use to detect the position. And then this shows you some scatter plots. And again, here you'll notice that with the mean, you already get very nice separation between the different positions. We also looked at the proximity sensor, and here again this was generally useful to detect if the phone is in the hand, but sometimes it gave us poor readings. So what we decided was why not fuse the readings from the proximity sensor. So what we found was the proximity sensor was very accurate in telling us if the phone was in the hand. Right? So if the proximity sensor tells us that the phone is in the hand, then we assume that's true. If this sensor tells reading indicates that this may not be in the hand, then we go back and look at the accelerometer, and then we trust whatever inference the accelerometer tells us. So that was the basic approach here. And in terms of the classifier, we just use a KNN because that's very simple to implement on the phone, and it worked. Right? So just stick with something that's simple. And this whole flow was triggered every delta seconds, and I'll show you results for different values of delta. Right? So in how long essentially we sample to make these decisions. Okay, the next issue was mapping the, yeah, okay.
I totally agree with you with that there are a lot of people, working like this. Most of them probably are sending SMS or writing SMS or browsing the web and looking at the map. I think it's possible to detect when the screen is on. And when the screen is on, it's probably a high probability that you have your phone in hand. So you think that it's just possible to avoid all the accelerometers and so on, and just say, when the screen is on, just take the sound pressure. Because there's a high probability that you have your phones in your hand. Because if it's your bag, the screen will not be on.
It can incidentally be turned on in the bag. It happens to me all the time.
Well,
I have a problem with my phone.
yes, of course, but I think that this is very important because your battery will drain out very quickly. And most of the phone, when it's not it's not in use, the screen is definitely off.
But you can accidentally do something in your bag to put this button and then it's on. So there is
that can happen. I agree with
to me all the time.
I agree with you, but then you can use the light detector. If it's dark, then usually it's black.
Yeah, I mean, I agree that this might not be the only approach, but this was fairly low. I mean, it doesn't consume a lot of energy to do the accelerometer measurements, and it was very simple to implement. And I have the results later, but I think we got very close to 90% accuracy already with this. So, yeah, but certainly we could look at that. Okay, the next issue was, okay, mapping this to a grid, right? I mean, yeah, certainly you could come up with noise measurements for each pinpoint location, but that won't scale, right? How do you do that for a large city? So we need to kind of discretize this and sort of overlay a grid over a city and then take measurements for each grid. So we tried out different grid sizes, right? So what we did was we did some measurements where we kept these phones at different with different spacings based on the grid sizes. And we saw, okay, what would be the difference between two consecutive grids in terms of the measurements as we varied the grid size. Right? So that's what we saw. Next, we looked at the acoustic standards, and we saw that the Australian acoustic sample, the body, recommends to use a grid system for making measurements, and they recommend that the difference between adjacent grids should be less than 5 dB when you decide the size of the grids. So looking at our readings, you can see that you could actually use any of these grid sizes. Right? Even this would work, that one is just very close to the threshold here. Right? But practically any of these could work. But then we went with the 10 by 10 grid because we found that there already exists a way to map the sort of Earth, map a grid onto the physical Earth using what's called a military grid system, which breaks up the Earth into grid sizes of 10 by 10, 100 by 100, and so on. So we could just use this existing method without having to reinvent the wheel. So we went ahead with this 10 by 10 grid size. Okay, now let me briefly talk of why we need to do signal reconstruction in the first place. Right? So imagine you have this road segment, you have these grids, A, B, C, D. Right? And imagine you're looking at 2 seconds of time. So let's say we have measurements from grid A for both instances, grid B only for one instance, grid D again both instances, but then we don't have any measurements for grid C at all. Right? So essentially, if you think of a noise map, it's actually a spatio-temporal map. Right? So you have space and time. So you can think of it like a vector essentially. And then you very clearly see that you have missing samples. Right? So you only have measurements here, for example, for 5 out of 8 points. So we do need to reconstruct the remaining samples. Now, how do you do this? So again, we used various approaches. So starting off with something very simple like linear interpolation, nearest neighbor, and to something which are more complex like Gaussian interpolation, and interesting approach based on this idea of compressive sensing, which uses this L1 minimization. The caveat being that if you want to use this, the underlying data must be sparse or must be compressible in one particular basis. And we found that environmental noise is actually sparse in the discrete cosine transform basis. So we could actually use compressive sensing. And I'll show you results a little later. Now in terms of implementing this, we started off, as I said earlier, using the Nokia phones before the current generation of smartphones were out there. But then we eventually graduated to Android. So our early systems were based on the N95 and 97, and then our recent versions are on Google Nexus 4S and HTC One. So the client was developed in Java on the Nokia phones. For the Android versions, we just used Android. The context classification was all done using Python scripts. The backend was a MySQL server. We used some PHP scripting, mainly for the connection manager on the backend. And all the reconstruction was just done using MATLAB, because that was most efficient. Remember, this is happening on the backend, not on the actual phones. Okay, now some results for the whole system. So this shows you the accuracy. Right? So this shows you a time series for the reference sound level meter and the mobile, the one on the phone. And you see that the shape of the waves are very similar as long as you correct for the calibration constant. So after applying the calibration constant, we got very accurate measurements. Okay, now the issue is how do you do calibration, right? Would a one-time calibration work, or do we need to recalibrate? So we found that certainly the calibration constant does drift with time. So can we actually come up with a system that the user can actually use and frequently recalibrate the phone? So we came up with an in situ calibration system. The idea was simple. We used Audacity to create various calibration tones. They were essentially sinusoidal waves of different frequency and different amplitudes. And we mixed some silence in it. Right? So we created a 5-minute tone which went through this sequence of 30 seconds of tone at a certain amplitude, 30 seconds of silence, and so on. And we asked the user to put the phone in a quiet room. So all the user has to do is go to a quiet room, start this calibration meter, let it play for 5 minutes. So it plays the tone, it records, and based on these measurements, it comes up with an offset. And then we saw how the offset actually drifts with time. Right? So this shows you measurements from 4 different phones. And we see that the offset is fairly okay for up to a month. After a month, it starts to drift with time. So what we do is we recommend the user to recalibrate once every month, which is not too much of overhead. Okay. Now this shows you results for the context classifier I mentioned earlier. Remember, our goal was to do measurements when the phone is actually in the hand and disregard other positions. So we tried out different features, different durations for how long we sample. And we found about 84% accuracy just using the mean, a 60-second duration, and then the number here indicates how often the proximity sensor actually fires within that period. So we got about 84% accuracy, which was the best result based on all these factors. So we went ahead with this particular choice. Okay, I'll skip this slide. I'll show you some data on the actual power draw. Right? So how taxing is this app on the phone? So this shows you data for the CPU usage for the various threads. So the top one is the more interesting when the app is running at max capacity, when it's doing the signal processing and the GPS lock. And we found the CPU usage was quite okay, about 36% on average, though the RAM usage was fairly high. And then here we looked at the power drain on the phone, right? So let's say we found that it takes about, say, 2.5 minutes to get the initial GPS lock, which consumes about 0.5 watt hours. Then it took about half a minute to do the context discovery, 0.312 watt hours. And then say 4 minutes to actually do a measurement. So we continuously measure the noise levels for 4 minutes. Right? So imagine that's a 7-minute cycle. Right? So assuming, let's say your battery is 5.6 watt hours. So if you were doing this constantly, the phone would die out in about 5 hours. Note this is very conservative in that we assume each time you need to get a GPS lock. In reality, once you get a GPS lock, you don't need to do it again and again. Right? And again, no one's going to keep measuring noise samples constantly for 5 hours. So clearly these numbers, the takeaway message is it's not very taxing on the battery, right, if you're doing measurements on and off. Now in terms of measurements, we went out and did some measurements in 2 locations. So one was a residential suburb where the sound levels were usually quiet, but then they increased during peak hours. And then a semi-commercial suburb which was adjacent to a very big road, a big highway. So here there was constant high noise. Right? And we did measurements both during peak and off-peak hours over a 1 hour period with 10 people walking around. So this is the actual ground truth, and that's the scale. And then here we show you the results for the reconstruction. And in this case, we are only showing you results for the compressive sensing strategy. I'll show you some other results later. So here, if you use only 10% of the samples, you clearly don't get a good accuracy. But then if you go up to 50, you're already coming close. And then if you assume 30% of the samples are missing, you already get excellent accuracy in terms of the noise map. Right? So this was for off-peak, and with peak, again, we observed similar behavior. Now this shows you a complete summary of the results for both peak and off-peak, and this is the RMS error. This is how much data we actually use for the reconstruction. So the bottom line here is we found that with about 70%, 60 to 70% of the samples, you're already getting very high accuracy for the noise map. Then we did some simulations. So what we did was we measured some noise profiles on a major highway near our university. We created 4 profiles. They differed in the spacing between the phones where we took the measurements. And then one particular profile had some varying traffic. So there was a sort of perpendicular road that spanned the road that we were measuring. So here, cars were going in and cars were coming out. So there was some variation in the traffic being measured. And we compared all the reconstruction strategies that I mentioned earlier, and we found that the best result was indeed for the compressive sensing strategy. Right? And that's kind of expected because that's a fairly advanced and known to be accurate strategy for reconstruction. Okay, so I guess that brings me to the end. So in this piece of work, as I said, our goal was to actually build a whole end-to-end system, and you've seen that we've looked at various aspects of this to generate a noise pollution map. I talked about various aspects of the system design. We showed that the phone can actually work as a sound level meter. We came up with this simple context recognition module to trigger the phone for measurements. And then we showed that you could actually reconstruct the profile with up to 40% of the samples missing using this approach of compressive sensing. So that's all I have to say. Happy to take questions. If not, I think we're perfectly on time.